Welcome to Lesson 6.1, the Function Notation Review. So to start off, we're going to talk a little bit about functions, which are basically special types of relation. Functions are a set of ordered pairs in which for every value of x, there is only one value of y. So now a relation is just a relationship between sets of information. So the way that we're going to check whether something is a relation or whether it's a function is a couple of different ways. The first way we can take a look at is the vertical line test. So basically, if you create a vertical line and then you take that vertical line and move it left to right through your function, if that vertical line only touches your function in one spot, then you can say that this is a function. Okay? If your vertical line intersects your graph at more than one point, so for example here and here, then this graph here would not be a function. There are other ways to tell whether something is a function or not. Let's say, for example, you had a table of values, and in our table of values we had x values, okay, and their corresponding y values. Again, I'm just making these up. Okay, you can see that in this, our x value of -9 has a y value of 13. Our x value, again, of -9 has a y value of 19. So here we have one x value with two different y values. So again, this, if we plotted it out, would not be a function. Those are two ways that you can tell whether something is a function or not. So we'll move on to example 1 here. So basically we want to state the domain and range and state whether the graph that we draw is a function. So the first thing we're going to do is graph. So we have a quartic here. So if I wanted to graph this, I would want to find my x-intercepts, my y-intercepts, and the direction of opening, so the end behavior. So if we found our x-intercepts, I would factor, and I know that this is a difference of squares. I would have x squared minus 4, and then x squared plus 4. And again, if I were to break this down even further, I would have x minus 2, x plus 2, and then we'll leave the x squared plus 4 alone. So if I wanted to find out where my zeros were, well, here I would have x equals 2, here I would have x equals -2, and here this is an imaginary root, so we can leave that alone. So the first thing I'm going to plot is our x-intercepts at -2 and 2. We can find our y-intercept, basically if you let x equal 0. So our y-intercept is -16. And because we have a quartic with a positive leading coefficient, I know that my end behavior, both ends will rise. So what we actually end up with is a skinny looking parabola. So clearly from our function, we can see that this does represent a function, because if we did the vertical line test, our vertical line test will pass. Okay, so now domain and range. For any parabola, it will expand in both directions, left and right, forever and ever. So we can say that x is an element of the real numbers. And then for our range, we see that we start at -16 and continue to rise up. Okay, so we'll move on to example 2, where we have x squared plus y squared equals 25. So basically what this is a circle. Okay, and if we figured out what r is, if we took the square root of 25, we know that the radius would be 5. So if we think about a circle that is centered at 0, 0, that has radius 5, it's going to fail a vertical line test. So therefore, this would not be a function, but just for fun, we can still do domain and range. Now, again, it's centered at 0, 0 with radius 5, so that must tell us that our x values only go between -5 and 5. And same for our y values. So our lowest point would be -5, and our highest point would be 5. Okay, so function notation, and we did touch upon this about at the beginning of the semester. We have two kinds of notation. The XY notation that we use quite frequently, and then we have function notation. Now the function notation is read as f of x or f at x. It's not f times x. Okay, so if we were to solve for f of 5, well, that means I'm going to substitute 5 for every x in the expression. So to solve for f at 5, I would sub in the number 5 and solve. So if we continue on, we would say, okay, well, we have 5 squared, which is 25, plus 10 minus 8. So then we can say that f of 5 equals 27. And now this is something that I see a lot, and I don't want this to happen, so I'm going to show you what I see, and so that way you won't imitate it. So again, a lot of people think that this is f times 5, and that for some reason they need to isolate for f. So they go ahead and divide both sides by 5 and tell me that f is equal to 27 over 5. Okay, so all of this here is incorrect. Okay, we don't do this. We stop at f at 5 equals 27. And what does this tell us? Well, that tells us that there is a point that lies on our function that when x is 5, our y value would be 27. Okay, let's move on to example 2. We want to find each of the following. So using that function notation, I want to substitute 0 for every x that I see here. So if I sub in 0 for every x, we end up with f at 0 equaling 1. So that tells us that 0, 1 is a point on the function. And actually this is a special point because when your x value is 0, we end up finding the y-intercept. Okay, let's try another one. F at 3. So again, sub in 3 for every x. And remember your BEDMAS rules. This is 2 times 9, not 6 squared. So 2 times 9 minus 21 plus 1. And we end up with negative 2. Okay, so we know that 3, negative 2 is a point on the function. And now part C, f at negative 1. So same idea, sub in. Okay, so negative 1 squared is 1 times 2. Negative 7 times negative 1. And so when x equals negative 1, y equals 10. So the point negative 1, 10 would lie on our function f of x. So first we're going to replace every x with a plus 1. And then once we're done that, we're going to multiply the entire thing by 4. So what we're going to do is leave the 4 on the outside for now, and then we're going to replace all the x's with a plus 1. Okay, so again, the 4 will just kind of go along for the ride for now, and we'll just expand and simplify inside the brackets. So this actually becomes 2 times, we'll expand a plus 1, well that's a squared plus 2a plus 1, and then we can expand and simplify further. So we'll take that 2 and multiply it in. It becomes 2a squared plus 4a plus 2. Take the negative 7 and distribute. And then the plus 1 at the end. Now at this point you can choose to simplify or you can multiply the 4 in. I'm going to simplify first. So we're left with 2a squared, 4a, take away 7a, and then plus 2 minus 7 plus 1. And then finally, I'm going to take that 4 on the outside and distribute it inside the bracket. Becomes 8a squared minus 12a minus 16. Okay, we'll moving on to example 3. This time we are given f of x and a g of x, and this time we want to find the values of x that satisfy the following. So basically, you are trying to solve for x when y equals some value. Okay, so a little bit different. This time we're not replacing all the x's. We're saying that the function f of x is set equal to 1. So in this case, I will move the 8 over, so 1 take away 8, and then divide both sides by 3. So in this case, we solved for x. Moving on. This time we want to set g of x equal to 0. So in this case, I'm taking a look and I see that we have a quadratic here that's set equal to 0. So if I want to solve for x, most likely I'm going to either factor or use the quadratic formula. So in this case, I want to find two numbers that multiply to negative 12 and add to negative 4. So those two numbers would be negative 6 and positive 2. And so we have two possible answers. X could be equal to 6 or x could be equal to negative 2. So in this case, when your y value is 0 or when your function is set to 0, you've just found your x-intercepts. Okay, and then in the last example, we have a couple of things going on. First, I do have a replacement of x in the function f. So I'm going to take our function f and replace x with negative x. So we end up with 3 times negative x plus 8. And I want to set that equal to g of x. And now g of x is x squared minus 4x minus 12. So in this case, I want to simplify and then most likely factor or use quadratic formula. Basically, you want to solve for x. So on our left side here, 3 times negative x plus 8 is equal to x squared minus 4x minus 12. And again, I see that we have a quadratic, so I'm going to move everything to one side so that we can factor. So minus 4x plus 3x, and then negative 12 plus or minus 8 will give us negative 20. So now in this case, we want to find two numbers that multiply to negative 20 and add to negative 1. Those two numbers would be negative 5 and positive 4. So to solve, we can say that x equals 5, or we can say that x equals negative 4. So that's it for today's lesson, and as always, if you have any questions, please make sure you ask in class. Take care, guys!